So in lesson 9.1, we are going to talk about systems of linear equations in two variables. Most of the time you do this in a high school algebra class. This is going to help prepare us for 9.2, which is, or maybe it's 9.4, I'm sure, 9.4, which is systems of nonlinear equations. Okay, so let's go ahead and get started with 9.1. So it says, to identify solutions to systems of linear equations in two variables. And it wants us to determine if the ordered pair is a solution to the system. For an ordered pair to be a solution to the system, it has to work for both equations, or however many equations you have listed, okay? And so first let's start with this one. We're going to plug the x and y value you see here. So where the x is sitting, we're going to plug in -3. Where the y is sitting, we're going to plug in 5. And then we're going to calculate it, and we should get an answer equal to 24. So that's going to be -6 plus 30, which is 24. So the first one checks out. Now for it to be a true solution to the system, it has to work for both. So now we're going to plug it into here, and so that's going to be our x value plus 5 times our y value, which is -3 plus 25, which is 22, not 3. So this is a big no. Okay, so -3, 5 doesn't work. If we were to graph them, the first line and the second line would end up intersecting at some other point if they intersect, and so not -3, 5. Now let's try the same thing for number 2. So this time the xy value we're going to try is 0, 1/2. So let's start with our first equation. So wherever I see x, I'm going to plug in a 0, and y is 1/2. So this is 5 times 0 plus 10 times 1/2 is really 0 plus 5, which is 5. So it works. So the first one works. And now let's see if the second one works. So that's going to be 22 times 0 minus 6 times 1/2, which is 0 minus 3, which is -3. So that one works. So it is a yes. Are there any questions about problem number 1 or problem number 2? Now, these are linear systems, excuse me. So if they are linear systems, we are talking about lines. So if we have one unique solution to a system of linear equations, the lines are just going to meet in an x of some sort, okay? So that's how we would get one solution. If there is no solutions, for the lines to never meet, they would have to be parallel. And infinitely many solutions would be like if you drew a line and then you drew the other line and you found out that they are exactly the same set of points, and that would have infinitely many solutions. So let me tell you what they call these things. If there is one solution, it is a consistent, independent type of system. So if it makes an x, if it were to graph, it is a consistent. That sure doesn't look like the word consistent. It is a consistent independent set. If it has infinitely many solutions, it is a consistent dependent set. And then if it has no solution at all, it is called inconsistent. Okay, So those are really the three possibilities. They cross, they never touch, or they overlap. Okay. There are two main ways that we're going to solve these. Yes, you can solve them by graphing, so you know that is always a possibility. But the algebraic ways that we're going to concentrate on are substitution, and I call it elimination. Substitution and elimination in some ways work similar, but kind of in opposite orders. For substitution, you're going to isolate a variable and then substitute that information into the other equation. For elimination, we are going to write the equations in the same format, and then we are going to line up the A's, the B's, and the C's, and our job is to eliminate either the X's or the Y's. And it's much easier to explain once we actually can do a problem. Okay? Okay, so let's go ahead and look at some examples to solve algebraically. Now, they've told us they want us to use substitution. So when I look at this, my first instinct is not to do substitution, but to do elimination. But they want us to do substitution, so let's go for it. In substitution, we have to isolate one of the variables. So let's get this variable that to me has the simplest coefficient. It's the simplest in general. Let's solve this equation for y. So let me write it over here. Let's subtract 5x from both sides and then divide off the -1. So in substitution, you have to have one of your equations need to say y equals all the other stuff or x equals all the other stuff. It doesn't matter. So I find the simplest variable and rearrange and solve. So this equation has given me this information. So now what are you going to do with it? Well, you're going to take the other equation, and where we see y, we are going to substitute in 5x plus 26. So this is going to be 2x plus 3 times that thing we are going to substitute in, 5x plus 26. It has to equal 10. So all I did was where the y was sitting, I replaced it with 5x plus 26. And now it's just a one variable equation, and so we can just solve it. So next we would have to distribute. Don't forget to distribute the 3 to both the 5x and the 26. Combine any like terms that you see, so I can combine those x's. Subtract 10 from both sides. And then divide negative 68 by 17, and we get an x value of -4. Now it's a system. We are looking for an x and a y that works for both of them. So we are not done. We have to take this information and plug it back in. Now, one really nice thing about substitution is we have an equation ready to set it into. We know that y is equal to 5x plus 26. So y is going to be 5 times that x value we just found plus 26. So now I'm just going to substitute that in right there. So substitution has technically like 2 substitutions to do. And so now we get y minus 20. Y equals -20 plus 26. So y equals 6. Now, it is an ordered pair. So write it as an ordered pair, -4, 6. Just write it alphabetically if they use other letters. And if we were to graph it, say, on Desmos, you should see that at the point -4, +6, we have intersected. And so that is an example of substitution. Any questions about example 3? Any questions about example 3? Okay. So now let's use the elimination method. Now, in the same problem that we saw before, like I said, my first instinct would have been to possibly eliminate them. Now, the first step in elimination is line up the x's, the y's, the equal to, and the numbers. So they should be in that order. X plus y equals a number. Okay? Now, they don't have to be exactly that way, but it's helpful that that's kind of the standard that you want to get. Now, we want to use rules of algebra to eliminate one of our variables. If we decide to eliminate the x's, we would use the least common multiple of 2 and 5, which is 10. If we decide to eliminate the y's, we would use the least common multiple of 3 and 1, which is 3. And so you decide what to do. Now, I like the fact that I'm going to change things to 3's, and this one already has a 3 sitting there. So because of that, I'm more inclined to make it 3's. But if it occurs to you to make the x's 10's, there's nothing wrong with that. You can do that. So I'm going to eliminate the y's. I really also like that my y's, one is positive and one is negative, because that's one of your goals. And so I'm going to multiply this equation by 3. And so I get the first equation I'm not touching. The second equation I'm going to multiply everything through by 3. So I get 15x minus 3y equals negative 78. And now we add the two equations together, hence eliminating our y terms. So now our y terms that have been eliminated. 2x plus 15x is 17x. Bring down your equals. Equals negative 78. So x equals negative 4. Now that's exactly the answer we got before, but it just appeared in a slightly different way. Now we have to take this value and put it into either one of these equations. It's really your choice, doesn't matter. Since this y is so nice and is just kind of simple, let's plug it into the bottom equation. So 5 times negative 4 minus y equals negative 26. Negative 20 minus y equals negative 26. If I add 20 to both sides, I get negative y equals negative 6. So y equals 6. Now look what we got before. We got negative 4, 6. Either method should end up resulting in the same final answer. Okay? Any questions about number 4? Let's look at example 5. Now, one really great thing about problems like this is these are equations you do have some control over. Now, I see decimals here. If you see fractions or decimals within the problems, you can use some tricks to help you. With fractions, we're going to multiply through by the common denominator to kind of get rid of the fractions. Here, with decimals, we're going to kind of multiply through by the denominator of the decimals, or the tenths place, hundredths place, or whatever the places of the decimals. Let me show you what I mean. It's kind of hard to explain. Now, they didn't tell us what system or what kind of system or solving systems that they want. They didn't say substitution or elimination, so you get to decide, whatever you decide to do. I don't like that these are decimals, so I'm going to multiply this by 10 because the longest decimal we ever see is tenths. So if I multiply this one by 10, I get 50x plus 3y equals 14. And the longest decimal I see here is actually the hundredths in that 28. So I'm going to multiply by 100, and I'm going to get 20x minus 10y equals 28. Now, looking at the original, or looking at this new version, The new version just feels a little easier to deal with, okay? So what can we do? Well, we can either turn the x's into the least common multiple of 50 and 20. Well, the least common multiple of 50 and 20 is 100. We could change the y's. The least common multiple of 3 and 10 is 3 times 10, or 30. So I think that's littler, and it might be a little easier. So to make this top number 30, and I'm talking about this term right here, I would have to multiply by 10. If I want to multiply something to turn that into 30, I'm going to just multiply that by 3. Now, not only do we want them to be 30s, but we want one of them to be a positive 30 and one of them to be a negative 30. They're naturally already one positive, one negative, so that's good. So let's do the multiplication I talked about. If I multiply the top equation by 10, I get 500x plus 30y equals 140. Now multiply everything on the bottom times 3. We get 60x minus 30y equals 84. Now I'm just going to add those two together because my 30y's are going to disappear because one's positive and one's negative. So I get 560x equals 140 plus 84, which is 224. I'm sorry, that's a 4. And then I need to divide by 560. So 224 divided by 560 does reduce down quite a bit. If you reduce that all the way down, you get 2/5. If you wanted to go back to that decimal sort of form, that's 0.4. Okay. So there's our x. Now we need a y. So I think this equation is probably one of my nicest. So I'm going to take out x and put 0.4 right there. And so I'll do it to the side here. So 50 times 0.4 plus 3y equals 14. 50 times 0.4 is 20. Divide both sides, or I'm sorry, subtract 20 from both sides. Divide by 3. And so we get x value of 2/5, y value of negative 2. Now you can give me the 2/5 or the 0.4, it doesn't matter, either would be correct. Any questions about number 5? Okay, now we find one with fractions in it. Now this one is set up, I think, pretty nicely for substitution, and the only fraction we see is in the substitution part. So sometimes I'll multiply through by 4, especially if I decide I want to use elimination. But in this case, we can't use elimination the way that it's set up. It's really ready to go for substitution. So let's take this and substitute it into the other equation where we see the y. So we get 2x plus 4 times that new y value, which is 5x minus 7/4 equals 4. Now that 4 that was sitting right here is in front of our y, so the 4 needs to distribute in. That's really good because we are going to get rid of that fraction. And so we get 2x plus 20x minus 7 equals 4. And now it's just, we'll combine our like terms and stuff. We get 22x equals 11. In that phase, all I did was add the 2 and the 20, got the 22x, and then I added 7 to both sides. And then our fraction is 11 divided by 22. Reduce it down and get 1/2. Now, one thing that's really great about substitution is we can take that half and plug it in right there. and then we'll get our y. So let's practice doing that. So y is going to be 5 times that x value minus 7/4. Now we have a problem here. We have a 5/2 minus a 7/4. We can only add or subtract fractions if they both have common denominators. So let's multiply this by 2 on top and bottom, so that first fraction will also be fourths. And so we get 10/4 minus 7/4 is 3/4. And now we have our x and our y, so please write it in an ordered pair. So that's 1/2, 3/4. Any questions about example 6? Okay, let's look at number 7. Now, right now we have a lot of things mixed up. So, well, let's do a little bit of simplify it a little bit. Let's take this 3 and distribute it in, and let's take this 6 and distribute in. Just kind of as a first step to see how it changes things. So we get 3x minus 3 plus 10 equals negative y for the first equation. We do have some like terms, so that's 3x plus 7 equals negative 1. So that's this equation. I've just tried to simplify it a little bit by distributing, combining like terms, and then we'll leave it for now. Now let's take a look at this one. Let's distribute in the 6 on the left side. We get 6y minus 30 equals 4x minus 28. So I just distributed the 6. Now there's a mixture of ways to do this at this point. Let's rearrange this one to be, they call it standard form. So the x comes first, then the y, then the c. Let me write that again. ax plus by equals c. So the a comes first, then the b, and then equals c. So let's kind of rearrange both of these so we get that familiar x plus y equals a number. And so this one we have to kind of relocate both of those. And so we get 3x plus y equals negative 7. And in this one, if we do that, let's put the 4x first, then the 6y. And then if we add 30 to the other side, it's going to become a 2. So now I'm going to focus on these two equations. So I just got them, look, I got them in the same order. The x, the y equals the number. The x, the y equals the number. Now the reason I'm going to do that is so that I can use elimination. So we can either change our x's to 12s, one a positive 12, one a negative 12, or we can change our y's to 6's. Now, one of them is already a 6, so I think a good route to go is to multiply this one by negative 6. So we end up with a positive 6 and a negative 6 to eliminate. So I'm going to multiply the red equation with the star next to it by negative 6. I get negative 18x minus 6y is negative 7. Now I'm going to multiply the green equation. Oh, I'm not going to multiply by anything. I'm going to just rewrite the green equation. Because what has happened here is that my y's are eliminated, and that's what we were trying to get, one of the things to be eliminated. And so we get negative 22x equals negative, no, that's not it, that's negative 5. And so x equals 5 over 22. Let me just check to make sure I didn't do anything funky. If anybody caught anything funky, please let me know. You sure would. Thank you so much. So a good point is, okay, so I multiplied this by -6 and this by -6, but I forgot to multiply that by -6, which would change things a little bit. Thank you so much. I knew something must have been wrong. So if we multiply -6 times -2, or -6 times -7, sorry, you get 42. Plus 2 is 44. And so we get -22x equals 44. So x equals -2. Thank you, thank you. Oh, I'm so glad you found it. Now, next. We found the x. We got to find the y. We can plug it back anywhere we want. I think this one's pretty easy. I think this one's pretty easy to plug into y. So let's stick our x -2 value right there. So it's going to go right in that spot. And so we're going to get 3 times -2 plus 7 equals the opposite of y. So we're going to get -6 plus 7 equals the opposite of y. 1 equals the negative y, so y equals -1. And if you write it in an ordered pair, that's -2, -1. So there is example number 7. Do we have any questions going on with number 7? Okay, let's look at number 8. Oh, we do have a fraction one, that's good. Let's look at number 8. So 8, I think, is a good substitution because it says that y is equal to this, so we can take out the y in the other equation and just plop it right in. So I think it's a really good way to use substitution. So we get 10x minus 5 times 2x minus 6 is 30. We're going to distribute the -5. We get 10x minus 10x plus 30 equals 30. And we got 30 equals 30. Well, what in the world does that mean? Well, that means that the x's don't matter. No matter what we get, we're always going to get a true statement, like 30 equals 30. What that means is this is a type of consistent, dependent type system. We can pick any x along the line and it's going to work because both these lines ended up duplicating themselves. They're actually the exact same line. And so what do you put for an answer? Well, you put all real numbers on the line. And you just write out one of the equations. So any real number or any ordered pair that is on that line would be a correct solution. So that's kind of nice for number 8. So if you get like 30 equals 30, it's always going to be all numbers or all points on the line. If you get something like 30 equals 10, then that's going to be a parallel system that there is no solution. So that's kind of the way that you can tell the difference. Any questions about number 8? Okay, let's look at number 9. Now, when I see fractions like this, I don't have to deal with them until maybe the end of my problem. So the only denominator in this one is a 3, and the only denominator of this one is a 2. So we can fix it really quickly, kind of like we did the decimals by multiplying by either 10 or 100. Let's multiply this equation by 3 and this equation by 2. Now let's watch what happens. When we multiply this top equation by 3, we get 3x plus 5y equals 1. Now if we multiply the bottom equation by 2 this time, I get 3x plus 5y equals 4. Now if this ever happens, where they were hiding kind of in. If they ended up being each 3x plus 5y equals 1, then that's the kind of system we just saw in number 8. They're actually exactly the same line. But if we get 3x plus 5y equals 1 and 3x plus 5y equals 4, they can't both equal 1 or 4. These are parallel lines. Now look if we tried to eliminate them. So let's say, you just didn't know that. I decided to multiply the bottom by -1. I end up getting 0 equals -3. That's not true. That will never be true. So these are parallel lines. This is an inconsistent system, and it has no solution. They have no points in common because they don't cross each other. Any questions about number 9? Okay, one last example. So here we have an application of systems that it's just wrapped in a word problem. Let's read it. David borrowed a total of $10,000 to pay for his final year of graduate school. He borrowed part of his money through his school with a Perkins loan that charged 5% simple interest, and the remainder of the money from his aunt at a rate of 1.4% simple interest per year. At the end of the year, he paid $428 in interest. How much did he borrow from each source? So let's call X the amount he's borrowed from Perkins, from his loans. And let's call Y the amount of money he borrowed from, was it his aunt? Yeah, his aunt. Okay? And so first, you always, when you're doing problems like this, is you have to kind of think out or write out, well, what variables am I going to use and what do they stand for? Now, they gave us 2 pieces of information. They gave us one piece of information about the interest, and they gave us one piece of information about the total. That's our system. We're going to have 2 equations. First, let's talk about the interest. For the interest, we have 5%, which isn't that, 0.05, times the total that he borrowed from Perkins, so that would be X. And his aunt only charged him 0.014 interest, so that's 0.041Y, and that total interest was $428. So if we add up the interest that Perkins charges, the interest that aunt charges, you're going to get $428. Now, how much total did he borrow? Well, that is the total he borrowed was $10,000. So you can see that we get a system of equations. Now, just like systems we saw earlier, if I see one here containing decimals, I look at my longest decimal. So this decimal right there is actually the thousandths spot. So to make this top equation a little bit nicer, let's multiply by 1,000. Because it's going to move the decimal place 3 places over, but we won't have decimals anymore. And so if we do that, we get 50x plus 14y equals 428,000. Okay? And now let's put the other equation underneath it. So we have a system of equations. Let's multiply this one by -50 so that we can get rid of our x's. So what do we get? Well, we get 50x plus 14y equals 42,000 or 428,000. Now, if I multiply the bottom by 50, oh, what am I going to get? I'm going to get negative 50x minus 50y equals a negative 5, 1, 2, 3, 4, 5. So it's going to be 428,000 minus 500,000 when I add them up. So I'm going to get, okay, let's see, what's 14 minus 15? 14 minus 50 is negative 36y. And then 500,000, negative 500,000 minus 428,000 is, just a minute, 72,000, negative 72,000. Divide off the negative 36, and I get y is 2,000. Now it's a word problem. What the heck does that mean? Well, this is the loan amount. Well, let's figure out how much he borrowed from his aunt. Okay? Well, we know that he borrowed $10,000 total. That's what this equation said, and that's what the word problem said. So the amount that, oh, I'm sorry, y stood for his, not his loan amount. Y stood for his amount he borrowed from his aunt. The X stands for the Perkins loan. So that is going to be 10,000 minus 2,000, or $8,000. So we have found what he borrowed from each source. Any questions about that one? Okay, one last example, and then we'll stop, take like a 3-minute break, and then we'll start 9-4. Any questions about example 10 before we move on to example 11? Okay, let's move on to 11. I'm going to put it down on this other page. Okay. It says, a plane flies from Atlanta to Los Angeles against the wind in 5 hours. Okay, so I usually will make a chart. I'm going to make a distance equals rate times time chart. And I am going to make this beautiful chart. I'm going to go from Atlanta to Los Angeles. And then I'm going to go from Atlanta, or I'm sorry, probably Los Angeles back home. Okay, so the rate in which we go to Atlanta to Los Angeles, we're going against the wind. So the wind is pushing back at us and making us travel a little bit slower. And so whatever the plane is going, so if the plane is traveling some r, we have to subtract the rate of the wind, and it says that we got there in 5 hours. Okay. That sure doesn't look like a 5. Okay, sorry my chart's so ugly. Okay, so the rate at which we go to Los Angeles is r minus w, the rate of the plane minus the wind, and because we're going to get slowed down, and it takes us 5 hours. The return trip with the wind, so our rate would be r rate plus w, is 4 hours, and the distance each time is 3,200 kilometers. So what do we know? Well, we did know distance equals rate times time. So let's set up our equations. So we know 3,200 equals 5 times r minus w, and 3,200 equals 4 times r plus w. Okay. Now let's do a little bit of fixing up in here. Let's distribute our 5 and our 4. So we get 3,200 equals 5r minus 5w, and 3,200 equals 4r plus 4w. And what we're going to do is use elimination. So let's multiply this equation by 4. I'm going to try to eliminate the w's. and this equation by 5. Now the reason I picked the w's is one is positive, one is negative, and it's just kind of a simple sort of process. Okay, when we do that, we're going to get 3,200 times 4 is 12,800 equals 20R minus 20W. And then 3,200 times 5 is 16,000 equals 20R plus 20W. We're going to add the two equations together. Now, when we add the two equations together, we're going to get 28,800 equals 40R. So the rate of the plane is 28,800 divided by 40. And so the rate of the plane is 720 kilometers per hour. Now, if you read the question, it says, find the speed of the plane in still air and the speed of the wind. Well, we have the speed of the plane. So the speed of the plane is 720 kilometers per hour. Let's find the wind. So let's just take, it doesn't matter which equation, but pick an equation, but I'm going to use this one. I am going to stick the 720 in where the R is sitting. So I get 3,200 equals 4 times 720 plus 4W. So let's solve it. Well, the way we would solve it first is distribute the 4 with the 720. We get 3,200 equals 2,880 plus 4W. Now you got to subtract this thing off because that needs to go to the other side, so you get the 4W alone. So 3,200 minus 2,880, it's going to be 320 equals 4W. Divide 320 by 4 and get 80. So the wind is 80 kilometers per hour. Now it's a word problem, so you could even explain that this is the plane speed and that this is the wind. And I could have even written that down above at the top, that R is going to stand for the speed of the plane, and W is going to stand for the speed of the wind, which I didn't do. I apologize for that. Any questions about this last example from 9.1? Okay, well that is